Yeah. So here it is the entry point of the initialization checker. The initialization checker, it has some state. So in this scope, it initializes basically the state of the check. And what we do here is for each, so a combination unit is just a source file. So for each file, we traverse the code in the file. What we do here is to, like, as you can see here in the traversal, we just for each definition. So member definition, it can be a class definition, method, or value definition. So we just store the body, that is the definition of the symbol, to the symbol itself. So we have this association here. And another thing we do is, like, we check for each class, if it is a concurrent class, we add it as a task. So as I just mentioned, we only check concurrent class because it's only possible to initialize concurrent class. So we may only have initialization problems related to concurrent class. So here we, for each concurrent class, we add the class to the basically a job queue. And after it traverses all the source code, and it will start performing the check. So that's the entry point in the main logic. So here, like, so as you can see, in the compiler check phase, when we call add task, it will add basically the class, like, to a working list. And then when we call check, it will just work on this working list. So it will check all the concurrent classes in the source code one by one.
Yes.
Yeah. So that's like the skeleton of the checker. Next, I think so we have thin abstractions like cold, warm, and hot, right? So that's the abstract domain. So we can have to see how they are encoded in the code. So in the code, we have a base class called value. That is the abstract value. How that is a base class for other for hot, cold, for hot, cold, and warm. So for hot, cold, warm, the meaning is exactly as in the paper. Hot values, they are transitively initialized. For cold value, it may have uninitialized fields. For warm values, for warm object, or we know all its fields are initialized, but it may reach some uninitialized object.
Right.
And we also have another abstraction called this ref. What is this ref? This ref, we can think it. So basically, when we check each class, one by one, and we know that when we are in the body of the constructor, there is the object, the current object, and the initialization that is represented by this ref.
Yes.
So this ref and warm, because they both these two abstractions, they have fields, right? And their fields may contain different abstract values. So that's why they are called a reference value, because in this abstract domain we have a heap. A heap is from a reference to objects, where objects is just a field, a symbol, and its abstract values. So that's the abstract domain. There is another thing. So because Scala has functions, so we represent the function literals with the function value.
Right.
What it contains is that it so that's the body of the function, and this value. So the function, we only care about the function if it is like in the constructor or in some method that is reachable from the that is called from the constructor. So it means it captures this value, the object and the initialization, and the class is where the function is located, which class is located in, and the environment is like so you might remember in this in our checker we make the assumption that all method arguments, normally in most cases method arguments, they have to be hard. It means they are hard. So we actually, the environment in most cases we don't need this because they are hard. We only need this in some situations, that is in secondary constructors, because you remember we support the feature where we pass non-hard values to constructors. It can be a secondary constructor. So in that case, if you are inside a secondary constructor and then it may capture the parameter of the secondary constructor, then we add environment here so that it can be easily to get the abstract value of the parameters of the secondary constructor. The last abstract value is a ref site. Basically, a ref site is just a bunch of abstract values. So in most cases, they originate from if expressions. For example, if we have we have an if expression, the two branches each return a different worm value, then we would get two worm values. And remember that the worm here, it can be two different subclasses of a common class, right? So we cannot merge them, so we have to keep them as a set, basically.
I see. Okay.
Yeah, so that's the abstract domain. And then the analysis. So I'll skip things here. The entry point of the analysis is evaluate. There are two main methods, and let me see. And there, maybe I should first go to the method init. So the method init, basically, it means, so that is the constructor. So that's the template. I think you already know it. That's their code in the class body, right? So this is the entry point of the constructor. So the analysis will start from here, and then when it starts here, it needs to know which class body it is in, and it needs to know what's the object is working with, right? Because in the constructor is working with only one value and one object for this, and it needs to which class is their class body. So what it does is like, if we ignore some technical details at the high level, what it going to do is like to first do a super constructor call. That's according to Scala semantics, because the current class may inherit another class and pass some arguments. So the code here, it follows closely the Scala language semantics. So I will not go into the details here, because it's actually quite subtle, because in Scala you can also have many traits. You can only have one subclass, that's easy, but you can also have many traits. The traits can also have inheritance between them, and there is you need to follow the order defined by their language specification. But so basically we are writing an interpreter for Scala, but it's not a concrete value interpreter. It's an abstract interpreter because it's working on the abstract domain. So at the high level, so what it does is that it will call the super call, go to the super class, and after the super class call has finished, it will execute the class body, right? So for the class body is very easy. So it will just, for each statement in the body, so it will ignore other definitions in the body. Like if it is inner class, it will be ignored because it has no significance, initialization significance. So it will check a field initialization here, and then it will evaluate the right-hand side of the field definition. So the var_def is a field definition, and if there are some errors, it will add it to the error, and then it will upstate the heap value. It will be an abstract value, and it will be stored there. And then it will do it for every field. And a class body may also contain code that is not a field is not a field definition. It can be any expression. So that's handled here. Basically, what we do is, so if it is a field, yeah, we just evaluate the tree and then store the errors. If it is not a field definition, it's just some method calls, for example, we just evaluate the expression. So that's one method, that is the entry point of the abstract interpreter, that is the constructor init. And as you have seen that beyond the init, we, for any expression, we call the method eval. That's another important method we have. So eval is here, and here we do some caching for performance and termination reasons. I won't explain here, but the main logic is handled here. If we ignore the caching, it's handled by the class cases. So let's see what is there. So as you can see, from the comment, the method cases, it handles the evaluation of different expressions in Scala. Basically here, like as you can see, we have a big pattern match on all the possible syntactic forms of Scala code here, and that's a skeleton. Basically, that's the main skeleton of the initialization checker.
Okay. Yes.
So yeah, I don't know at this point if you have any questions.
No, not yet.
Okay, so I think I won't go into every case, but I just pick two cases, and then we can go into our issue and to know where to fix it.
Yes.
So one case I want to show is about the assign.
Okay.
Because it's very, very special. So if we have an assign statement in Scala, you might remember from the paper that the initialization checker, it enforces monotonicity. And it has the rule that if we assign some value to a field of an object, we require that the right-hand side must be a heart of value. It has to be transitively initialized. That is handled here in this logic. So what it does is that, yeah, of course, it has to evaluate the left-hand side, because the left-hand side may also contain complex code. It may also contain blocks like in the prefix.
Yeah.
And eventually, when it will evaluate the right-hand side and check that it is hard. If it is not hard, so the code will report an error. So that's the way. You remember in the paper, it says, okay, we have the rule saying in assignment, it has to be hard, and this is how it's implemented in the checker.
Okay. Okay. Yes.
Okay. So yeah. So let's go to another case that is related to our issue, that is the method call. And so let's see, well, it is the method call, I think. This one. So in this case, it handles method call. We created a helpful extractor. So basically, it will extract the method and all the arguments here. So what we do here is to first evaluate the arguments and report any errors that is encountered, and then we will check. There are a lot of different cases, because it can be a super constructor call. So if we have a super call, we need to do something, and then you see eventually what we do is to get a abstract value, and then do this call. For other cases, yeah, it's possible that we encounter a constructor. In that case, the logic goes to call constructor, and it will eventually, because we can have two different kind of constructors, primary constructors and secondary constructors. Yes, and they will be handled in the method called constructor. And we may have identifiers which correspond to local method calls, things like this. So let's just focus on the case where we have this sum.apply. For sum.apply, I think it should be in, let's see, it should be this, I think, select quantifier. It should be this case, right? Because the sum.apply, we have this, right?
Right.
So here it means the ref should be a select, right?
Yes.
apply is the method. So what we are going to do, the check what it does is that it will first evaluate sum. Sum is a global object, and evaluating a global object, it should return a hard value. And then it will check the reference, the symbol of reference, whether it is a constructor call. And in this case, it is not, right?
Yes, it
Because
is not.
sum is an object. No, the apply is a normal method.
Method.
So it will go here, right?
Yes.
It will go here, and so the receiver has this type, and this is just the arguments here is just for error reporting purposes. So let's just follow this call. So it's the call on method. So it's this one, right? It's defined on the result. And then it will be forwarded to the method defined on value. So let's see where it is. So it's here, is this one. Is an extension method.
Yes.
So all so all the logic related to method calls are handled here. And
yes, this is the place we saw earlier. Yes.
This is the code we have seen. So we have seen this, whether something is a synthetic apply. And then we have the code here. We have some logic here, special logic here to handle, for example, as instance of, or some like methods that we think they're always safe, like not equal, that is NE or EQ, that's reference equality. We think they're always safe, so we ignore them. So the main logic is actually here, like
yes.
So we do a pattern matching on the value. For some dot apply this, the value. So remember the value, it is the receiver, right?
Right.
It's the receiver. So is a sum. Sum is hot. We know it's hot. So it means it goes here.
Yes.
We reach this case, and then the code will check that whether the method symbol, so here, whether it is a synthetic apply by checking the flags. And we know that is the case because the apply method is synthesized by the compiler. It has the correct flags. So this is true. This test is true. And then we reach this line. So basically what we do here is to get the class of the sum, because sum is an object. So here we're getting the component class of the object. And then we delegate it to the method instantiate. So, but as we mentioned, we don't want to, actually in this case, we don't want to delegate to instantiate, because we don't have a source code. That's the problem we want to solve, because currently if we delegate it to instantiate, we need so basically what we do here is the code we have is sum dot apply. And what we're doing here is to, instead of checking this, we ask the check to check this code.
Yes.
But currently the checker cannot do that because we don't have source code for sum. It's compiled by Scala 2, not by Scala 3 compiler.
I see.
So it means we cannot use this trick to make the example work. So what we do is actually want to use the parametricity. because we know that sum dot apply, it has a like type T, right?
Yes.
I don't know how to write this properly. It should be something like this, right?
Right.
This T is parametric. So if we pass a code value to the T here, we know that in the body of the method apply, it cannot access field
From T.
on a value that is parametric T, which has the upper bound any. So it's safe. It is safe as long as we treat the return value sum T as a code, right?
I have a question at this point, but ultimately, we would end up calling instantiate, right? If not here, then probably later, right?
I didn't get your question. Could you repeat?
I was saying, so we would eventually have to call instantiate, right? If not here, then probably later.
Yeah, that's a good question. So if we follow the approach of parametricity, we don't have the need to call instantiate because the reasoning by parametricity, it does not need to check the body of the body of the method, because we know that it can do nothing dangerous because of parametricity, right? Because you only know a value that has a generic type T with the upper bound any. If you are not an evil programmer, and then you in the method body you can not do anything interesting except putting the value, directly return the value, or put the value in some container.
Yes.
So if that's the case, then if we always treat the return value of the method as code, then we are safe. We don't need to check what you actually do with the value in the body. So it means we don't need to check how you instantiate the container. That is checked elsewhere when the container is defined.
So what exactly is instantiate doing here for the other case?
For that case, instantiate. So it will basically it will eventually go to the entry point of the init, right? You remember there is we defined a method init that handles initialization of objects. So here if we call instantiate, so there are many different cases. If in Scala we have a prefix. If we have a new expression, we have the outer, that is a prefix, and we have also constructor arguments. If all of them they are hard, it means if all of them are fully initialized, then by local reasoning, the result value must be fully initialized. We don't need to check the body of the constructor if that's the case. That is by local reasoning. So we don't need to check it. The saves time is modular, that's very good. But in cases where if any of the constructor arguments or the prefix, that is new prefix dot class, if either the prefix or one of the constructor arguments is not hard, then we actually need to go to the class body basically abstractly interpret the body, the constructor of the class to make sure that the body does not incorrectly use the parameters of the constructor.
I see. I see.
Yeah.
So, oh, okay. Okay. So,
yeah, that's
okay, so
that's the place where we get the warning, because so we would reach somewhere here, I think, because if we instantiate, the value is the outer is hard indeed, but then if the constructor is not hard, so we get a warm, and if we call the constructor, and then we don't have a source code, so we'll have a problem. So I think it is it's somewhere here has source code. We don't have source code, so we'll report a warning calling unknown. So that's the one where we get the warning.
yes. I see. I see. That makes sense. So instantiate is more or less like a full detailed check, right?
Instantiate, yeah, it depends on cases. But if some of the arguments is not hard, it's more detailed check.
Yes. Okay.
Yeah. So that's why we cannot call this, because we don't have source code. If we have source code, it should be okay. So we should not get the warning, because we know the constructor of the sum, it does not contain any code in the body. So it should be okay. In this case, we actually want to use the parametricity check, because we know one advantage of this reasoning by parametricity is that it does not require us to check the body of the method.
Right, right.
Yeah, so it means the we
will
just
not need to call instantiate.
Yeah, we do not follow the logic there, and still we know is safe to do so because of parametricity. So in terms of the changes to the code, actually we need to do something here to check whether we have source for the method, and see if it is a synthetic apply, and we have source code, we go this. Otherwise, we do the parametricity. That I think should solve our problem. Maybe we can try. So let me unshare my screen and we start doing something.
Okay. Okay, and you can see my screen, right?
Yeah, I can see it.
Okay, so we are here at select, and then we go to this guy.
Yeah.
Yes, and then this guy, and here we are. And check parametricity, and we need to do something here.
Yeah.
Right. Okay. So we need to do what we were doing inside here, which was getting to know if the source code was not there. So we can get that check outside. Where is that check? Hot and
yeah, you go call constructor, you follow call constructor.
This guy, call cold?
No, not this one. The 783.
783.
Yeah,
Call
follow this
constructor.
one called constructor. Right?
I see. And it is this guy, no source code available, and the source code check is here. So the
Yeah.
CTAR has it, and this value is part of argument symbol itself.
Yeah,
So
yeah.
if we,
For each symbol, we can check whether it has source code.
okay. This means, okay, need to go back. Where were we? So we're back here. So from the symbol itself, we can get it. And so the method is a symbol, right? Okay.
Yeah.
Okay. So we add a case beforehand.
Hmm.
Okay.
Or you can just add as the same line as is synthetic apply.
Oh, inside it. Yeah.
Not inside, just as the same line as
I see.
synthetic apply. I think it should work.
And is source
Has
has
source.
has source and
Yeah.
not, right? If synthetic apply and method does not have source,
Uh,
then
yeah, I was thinking something else. Yeah, you can go ahead. Yeah.
it's not okay. Okay. And then we check with do the parametricity check, right?
I was thinking, maybe we can, like, you can just enhance the condition at 9632. Oh yeah, at 630. To do under has source code.
Okay.
And if the method has source code, yeah, if it has source, then do this. Otherwise, it will. It's already handled the logic there.
True. Yes, it's easier. Yes.
I don't know if it works. I haven't tried. Maybe we can run and see if it works. If it doesn't work, maybe we need more.
Yes. So if we do this check, then instantiate, we will never fall into that case then. This case, the final case. So this would mean this check is redundant then.
We may get rich instantiate from other code.
Yeah. Okay.
For example,
Yes.
Yeah.
Yes, makes sense. Oh, no, okay. So it was 600. Yes. Okay. I'll test this code now. So before we were getting this error, calling the external method, right?
Yeah.
Now run again. 9795. 9795. it compiled.
Yeah, cool. We fixed the issue.
Yes, if the method has source, otherwise, we fall into the parametric check. So the parametric check, it
Yeah, we
checks.
can go. Yeah, we can go into the method and see what it does.
Mhm.
Yeah. So basically, it first get the type of the method, and then it for each parameter. So for each parameter, it first it just it promote the argument, because sometimes the argument is hard. So if it is already hard, we don't need to use parametricity. If all the arguments are hard, we don't need to use reasoning by parametricity. So we just
Sorry, what exactly does promote mean?
promote. So it will check whether the value is hard.
Okay.
So there are some. So we know that a hard value is always hard, right? That's the easy case.
Yes. Yes.
But sometimes a warm value is also hard.
I see.
Sometimes this value can also be hard. That is the case when, for example, if a class contains 5 fields, all of the 5 fields are initialized, and at the end of the last field, we have some more code, but we know that after the initialization of the final field, this ref it becomes hard, right?
Right.
Yeah, there are some cases like this.
Oh.
It can also be the case that if we have an inner class, for example, if we have an inner case class, and we just instantiate an instance of the inner case class, in the checker, initially it will represent the value as warm, because that is because the inner case class object, it captures the outer this.
Yes.
But actually, when we nick that object, we can go on to check that it doesn't explicitly use the outer this in its class body, so it's safe to promote that warm object to hot.
I see.
So that's what the method promoter does.
Okay, so it's okay. So it does a descriptive check and this analyze and resolve the ambiguity, right?
Yeah.
Okay. So and if the errors are empty, then it will just make it will just do the and. Okay, if no errors, then all args promote, right?
Yeah.
Okay, so it's like it accumulates into this guy for each of the parameters, for each of the arguments.
Yeah. So the flag will remember whether all arguments they are hot, basically.
Okay.
I think a better name is all args hot. Maybe you can do a renaming here. Like, I think it will be a better name, or not this one, the one above. All args promote instead of all args.
Yes.
I think it will be all args hot. Right. That makes more sense.
Yes. And then we're checking the info with info is the type information about the argument, right?
Yeah. Is but defined at the definition set.
So this type param.
Yeah. So what it does is like it check whether the type that corresponded to the argument defined at the definition set is a type of parameter.
I see.
If it is type of parameter, and then it goes on to check whether the bound of the type parameter is nothing under any.
Okay. Wait, what? Shouldn't it be the other way? Like, why is it not the other way?
Uh-huh. Yeah, it's not the other way. So that is a way to check that the bounds is actually any type,
I
because
see.
we know if
I
something is
see. I see. I
if
see.
any type is some type of the other type, by
Yeah.
reasoning,
It is
it
an,
can only
yeah.
be any type, right?
Anyway, yeah.
The same for nothing. Yeah.
Uh, uh, is there? I see the bounds check. Is there no equality defined on bounds? We have to use this trick.
Yeah. The reason is that in a subtype system, reasoning about type equality is actually subtle.
Okay.
We cannot
Yeah.
use reference equality, structural equality,
Mm.
and here because there are also a lot of aliases to types, right? And if we actually do this, we know we're always safe and it's
Yeah.
short.
Okay. 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 So. Okay. Okay. So it is just. Okay. We have
Yeah.
12 minutes. Okay. So if it is within bounds, if within bounds, then nil, else errors, and not other param contains. Okay,
Yeah.
all params exist. Param is not equal to info, and param dot type symbol is not equal to definition the class tag class.
Yeah, that's
Is
a
it?
very subtle case. I think it can be
Oh, class tag. Yes.
so
Okay.
so
Okay.
the so basically what that check does is to check that if a method takes multiple arguments, and it checks that if the current argument is type T, that is parametric, and then the other arguments, they are either of the same type T, or their types do not contain T. The reason for this is like otherwise we can have some unsoundness. For example, if we have a method that takes a argument of type T and another argument that is array of T, and in the body of the method, we just store the type the value of type T to the array. Then suppose that the array is hot, and if we don't check the body of the method, then that assignment wouldn't need to unsoundness, because basically the code will make a code object reachable from a hot object, which breaks the invariant of the initialization check.
I see.
And this check ensures that cases like that cannot happen, because you cannot assign a parametric value T to some other value that doesn't contain a parametric type T. So that's what the check does.
This is like an n square check. So for each type, we're also checking every other type. Okay. Okay.
Yeah,
Which
exactly.
is not U, and which does not have an info that occurs in param. So this is the array T, right?
Yeah. It checks. Yeah, it doesn't occur in the parameter. Yeah.
I see.
Yeah, actually in the PR, which you will be able to find from the issue we're working on, the PR for the parametricity, it contains test cases for unsoundness. Because if we don't have this check, we will it's easy to create programs that break the checker.
Right, right. Okay, okay. So we are saying, I see, the constructor can have a type T, but cannot have, like, let's say, a list of type T. Like, it cannot have both, but it can have,
You cannot have both.
but it can only have either T or just list of T, right?
Yeah, it can have two T's, or it may have a T and S, which the S and T, they're different type of parameters. That's also possible.
Okay, different type parameter, multiple type parameters, but not contained inside. Okay.
Yeah.
Okay, not in a type constructor. I see. Okay, okay. So if not other param contains, then nil, otherwise errors. And errors was the errors that came in from promoting the argument. I see. So we are okay, okay. I see. So additional errors will be written. Okay, after these checks. Okay, I see. Okay, so after this, after errors, so we return the errors, and if the all arguments are hot, right? So
yeah,
so errors will only be included here if it is not a type param reference, which makes sense, or if we have this inconsistency where we have T and list of T.
Yeah. If you scroll down a little bit, actually, I think there is a error in the code, because suppose at this line, let's rename this OArgs promote to OArgs hot. Because so if OArgs hot is okay to return hot, but if errors is not empty, not empty.
Shouldn't this be and?
It should not be and, but I was wondering why errors not empty, we return hard. Oh, I see. It makes sense. Yeah, because if errors are not empty, is fine. Because we're reporting the errors so you see the result is hard, but we're reporting the errors, right? That's also okay. Yeah.
Wait. Even if the result is not hot.
If it is hot, we can know if it is hot, then the errors must be empty, because from the code we know that
but if it is not hot, and if the errors are empty.
If it is not hot and the errors are not empty, then we report the errors and we treat the return value as hot. That's the convention in the checker. So it will not like report a lot of cascading errors. Like, so
I see. Because in the end, it is still a warning, right?
Yeah.
It's not like a error.
Yeah, it's like in the compiler, if it found a type error, it will replace the code with something like nothing. So it will not propagate the error elsewhere. So the user might, for usability, is not a good thing. If from one error it propagate to like a bunch of other errors.
I see. Yes. So even in that case, we declare it as hot and also propagate the errors.
Yeah. So we already recorded the errors, so it's fine.
Okay. Yes. Okay. Okay. Let's see. So when we're doing the hot check, we do not do the T and arity check.
T and
Arity, that this check info occursion.
yeah, we included here right at 2619.
2619. Line
619. Yeah, it's
Oh,
just
sorry.
here. 619. So it's here.
Then nil else errors. Okay. No, I was saying we do not declare it as not hot, given this guy. If this guy returns,
that's fine because hot there are two orthogonal like concern like for hard for the flag or args hard, we only care about whether promotion is successful or not. If promotion is successful, it means there are no errors and the value can be considered hard. So in that case, if all args are hard, then we know the method call is always safe and the return value should be hard by local reasoning.
I see.